Hurricane Milton barrels toward the Florida coast, bringing winds of over 150 miles per hour. Entire cities brace for impact as the powerful storm approaches, threatening lives and causing widespread damage. But how does a storm like Milton begin? What forces come together to create such a powerful hurricane? In this video, we'll explore the science behind these destructive storms, how they form, and why they become so intense. Using Milton as a case study, we'll uncover what it takes for a tropical disturbance to evolve into a hurricane capable of reshaping entire landscapes. Let's dive into the journey of how hurricanes form. Hurricanes, like Milton, all start in the same way, as a tropical disturbance over warm ocean waters. These disturbances are clusters of thunderstorms, but for them to develop into something more powerful, they need the right conditions. First, the ocean's surface must be warm, at least 26.5 degrees Celsius, 80 degrees Fahrenheit. The heat from the water evaporates, creating moisture in the atmosphere. As this warm, moist air rises, it cools and condenses into clouds, releasing energy in the process. This energy powers the storm, allowing it to grow. But that's not enough on its own. To form a hurricane, the storm also needs rotation. This is where the Coriolis effect comes into play, caused by the Earth's rotation. In the northern hemisphere, it forces the storm to spin counterclockwise, giving it the signature spiral shape that defines hurricanes. As the storm strengthens, air continues to rise and flow outward from the top, causing even more air to be pulled in from the surrounding area. This creates a continuous cycle of rising air, cooling, and condensation, leading to further intensification. With favorable conditions like low wind shear and plenty of moisture, a tropical disturbance can evolve into a fully fledged hurricane, just like Milton. The journey from a simple tropical disturbance to a hurricane is complex and depends on a few key factors. After warm ocean waters fuel the storm, it reaches the next stage, a tropical depression. At this point, the system has a defined rotation, and winds reach speeds of up to 38 miles per hour, but it's still not strong enough to be called a storm. As more moisture is pulled into the system, the winds intensify. When sustained winds exceed 39 miles per hour, the storm is classified as a tropical storm and is given a name. This is when Milton officially became a named storm. But it doesn't stop there. With continuous energy from the ocean and favorable environmental conditions, tropical storms can grow even stronger. Once wind speeds hit 74 miles per hour, it becomes a hurricane. Now that Milton has reached hurricane status, let's take a closer look at its structure. At the heart of every hurricane is the eye, a calm area of low pressure at the center of the storm. Surrounding the eye is the eye wall, where the most intense winds and rain are found. This is the most dangerous part of the storm, with wind speeds often exceeding 150 miles per hour, as was the case with Milton. Beyond the eye wall are the spiral rain bands, which stretch out for hundreds of miles and can cause intense downpours and gusty winds even far from the storm's center. The larger the hurricane, the more extensive these rain bands are. This structure allows hurricanes to impact vast areas, sometimes even affecting multiple states. For a storm like Milton to become a powerful hurricane, the right environmental conditions must exist. The first is low wind shear. Wind shear is the difference in wind speed and direction at different altitudes. If wind shear is too high, it can disrupt the structure of a developing storm, preventing it from strengthening. In Milton's case, low wind shear allowed the storm to maintain its tight spiral structure and continue intensifying. The second factor is sea surface temperature. Warm waters provide the energy needed to sustain the storm. Milton fed off the unusually warm waters in the Atlantic, which were well above the 26.5 degrees Celsius threshold. As long as the storm stays over these warm waters, it can continue to grow. Finally, high humidity levels in the atmosphere provide additional moisture for the storm, further fueling cloud formation. These conditions helped Milton transform from a simple disturbance into a full-blown hurricane. When Hurricane Milton made landfall in Florida, it began to weaken. Once a hurricane moves over land, it loses its primary energy source, warm ocean water. Without this fuel, the storm's winds begin to slow down and the system starts to break apart. However, the danger doesn't end when the storm hits land. Milton's strong winds caused significant damage to buildings and infrastructure. Storm surges, or the rise in sea level pushed by the hurricane's winds, flooded coastal areas, causing severe damage to homes and businesses. Even after the winds died down, the heavy rainfall from Milton led to flash flooding, which posed a threat for days after the storm had passed. One of the most dangerous aspects of any hurricane is the storm surge. As Hurricane Milton approached the Florida coast, it pushed a massive amount of seawater inland. Storm surge can raise sea levels by as much as 10 to 20 feet in some cases, flooding homes and roads and causing widespread devastation. In addition to storm surge, hurricanes like Milton bring torrential rains. These heavy downpours can lead to inland flooding, even in areas far from the coast. During Milton, rainfall exceeded 15 inches in some areas, overwhelming rivers and drainage systems, making the storm's impact felt long after it had weakened. As the planet continues to warm, hurricanes like Milton may become even more intense. Rising global temperatures mean warmer ocean waters, which provide more fuel for these storms. Scientists are studying how climate change is affecting the frequency and intensity of hurricanes. While there may not be more hurricanes each year, the ones that do form are likely to be stronger, with higher wind speeds and heavier rainfall. Additionally, rising sea levels caused by melting ice caps increase the risk of storm surge flooding in coastal areas. As sea levels rise, the damage from storms like Milton could become more severe, putting more people and infrastructure at risk. Hurricane Milton is just one example of how powerful and destructive these storms can be. Understanding how hurricanes form and what factors contribute to their growth helps us better prepare for future storms. From the warm ocean waters that fuel them to the atmospheric conditions that allow them to grow, hurricanes are a reminder of the immense power of nature. As climate change continues to affect our planet, studying these storms is more important than ever. Thanks for watching. Make sure to like, share, and subscribe for more videos on the science behind natural disasters. Stay informed and stay safe during hurricane season.